So this project is related to numerical solution and control for satellite formulation flying with the EKF based navigation in MATLAB. So in this project, basically we are just discussing the satellite formulation flying enables a high resolution space mission through the coordinated operation of multiple spacecraft, but requires a precise modeling, navigation and control in a perturbed orbital environment. So basically in this complete MATLAB implementation, we are just focusing on the integrated dynamics, estimation, and the control framework for autonomous satellite formulation flying using in MATLAB. So we have just used a linear quadratic regulator provides baseline stabilization, while a model predictive control strategy ensures a fuel optimal trajectory tracking under thruster saturation constraints. So the EKF mean extended Kalman filter basically employed for onboard state estimation using the range and range rate measurements accounting for sensor noise and model uncertainty. So that's why the proposed framework highlights the effectiveness of the combining predictive control and state estimation for autonomous satellite clustering missions. So here is the abstract with the keywords and the introduction. Introduction basically provides us a relative motion according to satellite formulation flying. Like satellite is moving in terms of this like we called it a relative motion, and this is basically circle movement, okay, in the around this type of circle movement, okay. So here is I have just defined the physical constants used in the satellite formulation, which is parameters like how the orbital attitude, how the radius of earth gravitational parameters, which versus the constant of J2, and the Hill Clohesi Wiltshire state matrix basically defined as well, okay. So next one is basically how the CW control input matrix and defined in the column and its parameters as well. Hell Colsey Wiltshire basically one of the scientists who's commonly employed to describe the limitization of relative dynamics about a circular reference of orbit. So next one is basically just a second. Okay. So here is the satellite formation flying control center with the EKF based navigation. So basically EKF is widely used to estimate the techniques during the computational efficiency and capacity to handle the nonlinear measurement models. And here is the basically motivation background versus motivation according to model predictive control, orbital um, perturbations, gravitational non-uniformities, differential drag, and atmospheric effects continuously disturb relative motion, dynamics, and estimation challenges as well, which is basically related to low Earth orbits and remain the standard basically in many control studies. And we have to discuss its how the real world disturbance sources and unmodeled dynamics introduce uncertainties that degrade control performance if not properly addressed. So here is a control strategies and study objectives. Like these are the weighting matrices, LQR weighting matrices. LQR basically linear quadratic regularity, and the simulation framework development, basically, which is in which I have just added the closed loop architecture links the estimator outputs directly to the MPC and LQR controllers, performance metrics, and evaluation. So here is basically I have defined how performance comparison between the LQR fallback control with MPC based guided guidance highlight the advantages of predictive optimization. Validation and the practical implications basically defines how the EKF consistently converges to sub-meter level navigation accuracy, providing the reliable feedback for predictive control. So the problem statement basically, which is basically we need to maintain the precise relative positioning for multiple satellite in formulation of challenging tasks due to combined effects of nonlinear orbital dynamics, gravitational perturbations, and the environmental disturbances. So, therefore, there is a critical need to develop the integrated framework that combines the accurate dynamics modeling and robust state estimation and constrained optimal control strategies as well. Here's the mathematical model which we have just defined according to the dynamics of circular orbit. Here's the complete equations used in the linearized continuous time dynamics. And yes, methodology defines the linear quadratic regulatory with the stabilizing the feedback baseline, and the MPC parameters are attached with the provided in form of table, and MPC basically solves a constraint finite horizon optimization problem to minimize the state deviation as well as the control effort under the actuator saturation. So here is the design MATLAB simulation analysis in which I have defined the complete LQR method which basically stabilizes the feedback while a finite horizon model predictive control ensures the optimal trajectory and tracking through the matrices. Okay, here is basically phi. We need to consider it phi and the gamma values and EKF Range-Kutta method as well as the LQR methods as well. Okay, so here is a relative motion of satellite providing the output results in MATLAB trajectory. Next one is relative position according to the time as well as the MPC controllers work in tandem to reduce overshoot oscillations, relative velocity, and the thruster commands as well. Okay, formation of distance error, and this one is phase plane radial motions, and then results and discussions as well with the parameters of EKF configuration parameters and the conclusion versus references. Let me just show you the MATLAB demonstration how satellite formulation flying developed in MATLAB and how we will get the output results as well. Okay. These are the MATLAB functions defined. Always make sure always all the MATLAB functions should be defined at below of the code because the functions will only call during the code and will used in during the code, but when we just defined the function in during the code, it will provide us the error. Okay, and during the running of MATLAB. So that's why we need to provide all the functions in the below of MATLAB code. So let's wait and then we will get the output results accordingly. see the total change in voltage versus final position error versus orbit period as well. Okay, so here is the output results. Let me just show you. These are the relative motion. This is the relative position output graph, relative velocity, thruster commands, formation of distance error, and the phase plane radial motion according to the x dot meter per second. Like x dot is speed basically. Okay. So if you need to ask anything, you just ask me. I will answer your questions. Thank you.